pretend to be an accountant and write accounting software. You can work with scientists and pretend to be a scientist. So I look at computer science as sort of a chameleon type of occupation. And there are so many interesting projects here at ERDIC. I'm just really happy to be a part of it. So thank you all for coming this morning, and I hope you learn at least a little bit more than you knew when you walked in the doors. So we will be talking about Pareto Front for aircraft design optimization, and I'll give you an idea of the topics we're going to look at. So in developing the presentation, one of the things that kept coming up was, how do you talk about topic A without talking about topic B first, and how do you talk about topic B without talking about topic C? So what I want to do is try to lay out a roadmap that has a little bit of all of the different subjects involved in the Pareto Front algorithm, which is really the focus of the presentation. So I'm going to start talking a little bit about design methodologies. Not very much, but enough to give you the background so that when we get into Tradespace analysis, the project that we're working on, which is the LCAAT project, and of course the Pareto Front determination, you'll have a better idea of why we're doing some of the things that we're doing. Finally, we're going to talk about TradeAnalyzer, how we get Pareto Front optimization scripts into TradeAnalyzer, and then we'll show you where we plan to go from here. Okay, so just a brief introduction to set-based design methodology. First of all, I'm not a systems engineer. Some of you may be in here, so if I make any mistakes, please forgive me. But I do want to give you sort of an overview so that you see where these large data sets, large trade spaces that I'll be talking about are going to be coming from. So I'm going to talk now a little bit about set-based design, and this is going to be in contrast to some of the more traditional design methodologies, which include point-based design. So to start out, a point-based design is a methodology that takes an existing design and then tries to make some modifications or changes to it in order to reach new objectives. So for example, maybe you have a perfectly good car that's been designed, manufactured, you know that it's an acceptable design, but now some of the objectives have changed. For example, maybe you need better fuel economy. Maybe you need it to carry more passengers. So instead of scrapping the car that you know works for some situations, you take a good design and then you make modifications to it in order to accomplish the new objectives. That's point-based design. One of the problems with point-based design is that early on you have to be committed to a lot of the design decisions, which leads to less resilient designs. So when you try to make modifications later on, it becomes much more difficult. Set-based design ameliorates some of these problems that are inherent with the point-based design strategy. So in set-based design, one of the primary features is that we defer the detailed specifications until the trade-offs have been better studied and are more fully understood. And set-based design follows these basic steps. First of all, the design space has to be defined, and this is done by subject matter experts who truly understand the design space. So what you have to do is come up with a set of design variables that are the most impactful on the type of design that you're trying to come up with. Once a design space has been defined, then the alternatives can all be defined in parallel. So in this case, you're coming up with lots of different designs in parallel. You're not doing it sequentially where one design is based on a previous design. Okay, and because you come up with such a large set of designs, one of the primary steps in set-based design is being able to reduce that trade space. So at some point, you need to be able to remove any of the infeasible or the suboptimal designs that have come to be from the trade space itself. Another advantage is that you can iterate on different objectives. For example, the engineers may have different objectives than a team that's concerned primarily with manufacturability or producibility. So you can have different teams with different objectives for a particular systems design, and those teams can work in parallel. They don't have to wait for another team to finish before they proceed with their design process. And finally, as I've mentioned before, commitment to a design can be delayed until all of these studies have been performed. And so you're not committing up front to a design that's going to be very difficult to change later in the process. And this is just a spiral example of the steps that we just looked at. And so we start with defining the problem. We have an engineer or subject matter expert who understands the design space and is able to clearly identify design variables that are going to impact the design. Generate a large number of designs. Step number 3 is where we're going to remove any of those designs that are determined to be suboptimal or infeasible. We take a design, we continue with it, and the process proceeds like this. So one of the primary differences in the traditional point-based design and set-based design is that with point-based design, you're really constructing the design. So you have to know what you're doing. You're starting out with an existing design, you're making modifications to it based on some type of expertise, and you're considering all of the design variables together along with their interactions. On the other hand, with the set-based design methodology, we're looking more at design discovery. So you're discovering designs that possibly you never would have come up with a traditional approach. Set-based design offers flexibility for continued system refinement because you're not locked in early in the process. Allows you to proceed concurrently with different teams having different objectives. And again, it defers a detailed specification until trade-off studies have been performed so that you more fully understand what you're gaining and what you're losing with various design decisions. So this brings us to Tradespace Exploration, or TSE. So Tradespace Exploration is a resilient design methodology for large systems. What we have is a set of enumerated design variables that the engineers have come up with, and from these we've generated a large trade space, which consists of the set of all the possible design options. Now, most often this trade space is stored in a CSV file or an Excel spreadsheet, something that I'm sure is familiar to everybody here. So here we have a spreadsheet, and we have the columns. The columns consist of the design variables, and each one of the rows is considered to be a different design. So we have rows and columns, very easy to understand. Each row is a design. So the question becomes, how do we evaluate all of these different rows to determine which of these designs is going to be better for the purposes that we have in mind? Well, what we want to do is take this trade space and evaluate it in terms of cost versus utility. So for each one of these design points, we want to know what are we getting from it and what do we have to pay to get that functionality. Well, if you look at that simple example there, you see we have multiple columns, many different rows, and the question becomes, how do you really say which one is better? So if you look at the second or third column, you may pick one design. If you look at the fourth or fifth column, you may end up picking a different design. How do you know how to evaluate the trade-offs among all of the different designs in order to pick the one that's going to be best? So what we have are value functions that can take all of the different design variables, or possibly a subset of the design variables, compose those into a single utility measure. Okay, so in that case, you would only be looking at a single measure to be able to evaluate all of the designs against one another. So here's another way of looking at trade space exploration. It's really a balancing act. So if we have a scale that's trade space exploration, on the one side, we're going to be looking at what we get out of it. So these items on the right-hand side can be categorized into 3 different categories. We can look at capabilities of the system, we can look at performance measures of the system, and we can look at effectiveness measures of the system. Now that forms one side of the scale. So what are we looking to balance this against on the other side? Typically it's some type of a cost. Often it's life cycle cost. So for each unit that's produced, how much is this unit going to cost us for the entire life of that particular unit? It could be production cost, it could be average fixed cost, it could be some other measure. but this is a very standard type of way of looking at trade space exploration and trying to pick designs, which is a balancing act between some measure, such as cost, and the capabilities that we're going to get from each one of the designs. So we're going to look at each one of those components, the trade space exploration components, in a little more detail. Because if you're like me, when I first started this project a couple of months ago, last year, all of these terms that I'm using now would have gone right over my head. I wouldn't have known anything that anybody was saying. Okay, so when we talk about capabilities in terms of trade space exploration, what we're looking at are normally the physical characteristics of the system. So for the example that I'll be using in the presentation today, this is aircraft design. We'll be looking at design variables that include things like wingspan, the wing sweep angle, the fuselage length. If it's a combat vehicle, you might want to know what type of weapon is going to be included on the vehicle. So when we look at capabilities in trade spaces, we're talking basically about physical characteristics that comprise the design variables. Now once we have the design variables, what we can do is take the combinations of those in some type of a model, and we can figure out what performance measures we can generate from each one of the combinations of the physical characteristics of the system. So performance is going to give us operational values that are based on those physical characteristics. So again, for an aircraft example, what we would be looking at are things like, given a particular set of design variable values, how fast will this aircraft fly? What's the maximum altitude it can reach? What's its maximum range? Those would be our performance values that we're looking at. And our final component is effectiveness. So we have capabilities, we have performance, and now we're looking at how effective would each one of the designs in the trade space be in a particular relevant mission scenario. So this is very important because if we looked only at the performance measures, we might end up with an aircraft that had great range or great speed. But when we place that aircraft into a particular mission scenario, we may find out that we don't get the results that we wanted. So effectiveness measures tell us how well a particular design will perform in a scenario that's very similar to the one that we're looking at putting it into. And effectiveness measures typically come out of things like modeling and simulation software. So that brings us to our motivating example, our motivating project. Dave mentioned ERS. So ERS has been working with the Air Force Research Lab on a project called LCAAT for, I believe, about a year now. It had started a little bit before I came on board. And so I know when I first started, I heard LCAAT in the hallways, heard it whispered in rooms, and wasn't sure exactly what it meant for a while. So we're going to look at what the LCAAT project is in high-level terms. So LCAAT, first of all, stands for Low-Cost Attritable Aircraft Technology. We'll talk more about all of those words in a few minutes. But basically, it's a new design concept for military drones. The goal of LCAAT is to develop a low-cost, attritable aircraft design and manufacturing concept costing less than $3 million. Okay, so when the acronym LCAAT is used, it's often used in two different ways. So the program itself is, as the statement there on the screen says, it's a manufacturing concept, design and manufacturing concept. So we can use LCAAT in terms of this whole process of coming up with a design and manufacturing concept. But also we tend to use LCAAT to represent the product that will actually come out of it. So you may hear people say something like, well, what if we have 5 LCAATs? Okay, so you'll be able to tell the difference. I'll probably use it in both ways. But this is the introduction to LCAAT. Now, the motivation for this new manufacturing and design concept is fairly self-evident. If we look at manned military aircraft, I'm sure all of us know intuitively that these are incredibly expensive. So one of the figures that I found said that, for example, for an F-35, we're looking at over $100 million. Okay, if you lose an F-35 in a mission, you're not only looking at losing $100 million, you're also looking at losing the pilot. Okay, so you've lost a valued member of the force. You would probably have a search and rescue accompanying the downing of the aircraft. So manned military aircraft are very expensive. We want to try not to lose those. In contrast, we have existing drones or UAVs that are not as expensive. So here's a list of some that I found: Predator, Reaper, the Gray Eagle. You can see that all of these are considerably less expensive than, say, an F-35. However, just because they're cheaper doesn't mean they're expendable. Okay, so if we lose one of the drones, it's not a happy day because they're not cheap by any means. So now we'll start analyzing the acronym LCAAT. So the only thing that most people are puzzled by is the first A, attritable. In fact, it's often spell corrected to attributable, okay, but it's not, it's attritable. So what does attritable mean? Well, everybody's probably familiar with the word attrition, and most familiar with it in terms of workplace. So we often hear things about workplace attrition, which refers to an expected number of people are going to retire, an expected number of people are going to move to other jobs, leave the workforce for some reason. And those are sort of predictable, okay? You expect to have those types of losses. So that's referred to as attrition. Okay, I found an Air Force definition that uses attrit as a noun and says that it can refer to an expected rate of loss or attrition. So when we talk about a low-cost, attritable aircraft technology, we're looking at something that we kind of expect to lose. Okay, so the LCAAT, one of the LCAAT missions is to have it inexpensive enough that the loss is not really that impactful. It is designed for multiple uses, okay? So it's not a paper plate that's just going to be thrown away after each mission, okay? But it is going to be expected to have a shorter lifespan, so it'll fly multiple missions for a shorter period of time, and there's going to be little ongoing maintenance. So this is not something that we're going to spend a lot of money on trying to maintain in between flights. And one of the con-ops for the LCAAT is to use these en masse in order to add a low-risk, low-cost advantage in combat situations. So you can imagine if we send in 10 LCAATs, we would probably get some benefit from them, and if we lost all 10, it's only $30 million versus a single F-35 at over $100 million. So that's the idea behind LCAAT. So AFRL has been working on the LCAAT design, and the ERS people have been in contact with them. So throughout the design process, we've been learning more about how they work, and we've been working on the data sets that they've been generating. So the LCAAT design space is designed around 9 input parameters. So if you remember when I talked about set-based design, I was saying that somebody has to know something about the design space in order to be able to define these input design variables. So they settled on 9 design variables and 5 objectives. So on the 9 design variables, they ran a multi-objective genetic algorithm, and the objective for the genetic algorithm is given over on the right-hand side. It's very simple. We have 5 objectives. We're trying to minimize the aircraft flyaway cost and the takeoff field length, and we're trying to maximize the range, the speed, and the turn rate that we can get from the aircraft. Okay, so running this multi-objective genetic algorithm on the input variables generated a trade space of just over 270,000 different designs for LCAAT. So the designs are values are combined with the objective values. So we end up with the trade space consisting of 14 columns. We have the we have the 9 input variables, and then we have the 5 objective variables. So each row of the trade space consists of those 14 values. So here we are. We have a CSV file, we have rows, over 270,000 rows, and we have 14 columns. So the question becomes, now what do we do with it? Out of 270,000 designs, how are we going to pick a good one? This is where we come into the Pareto front. And this is where TC would be standing up here, except that he was unable to be here today. So I'm going to attempt to give this section. If you have questions, I'll try to answer them. But TC started on this work before I was part of the project. He was actually working on the Pareto fronts. So the Pareto front comes into that third block in the diagram for set-based design. At this point, we know with over 270,000 design points, all of them are not going to be good ones. So how do we eliminate the ones that are not good ones and find a set that's going to give us at least some type of optimality in the design? So first of all, what is the Pareto front? The Pareto front is going to consist of all the design alternatives that are not dominated by any other. Now, I know what your question is going to be. So here's the answer. What does it mean not to be dominated by another? So we say that a design alternative dominates another if it's as good or better for all the objective functions and better for at least one objective function. So you can turn that around. It's a little easier to understand, I think, if you think of it as being of the 5 objective functions that we talked about. If you have a design where one objective value is better than all the rest, is better than the others, and the other 4 values are at least as good, then you have a point that's on the Pareto front. Okay, what this gives us is it tells us that any alternative design that's not on the Pareto front can basically be eliminated, because for any of those values, you have another design point that is actually more optimal based on the objective functions that you gave it. So here are some of the advantages. Okay, first of all, if you've been in any type of modeling and design work, perhaps you've been a part of trying to create some type of really complex objective function that's going to tell you from a combination of many different values which one is better than the other. Okay, by using Pareto fronts, we eliminate the need to create some type of complex multi-objective function, and we can replace that with using these very simple objective functions, but we have multiple ones. So we're actually considering them basically in isolation, not really in isolation, but there's no need to consider the interactions of all of the values in order to come up with a complex function. So that's one advantage. And once the objective functions have been defined, the Pareto front can be computed, and there's no other need for some type of subject matter expert to come in and analyze the set based on some other criteria. So we create the objective functions because we know what it is we're looking for. The Pareto front can be computed, and at that point we know that the design points that lie along the Pareto front are going to give us our best values based on the objective functions that we gave it. So here's an example of some points to help get the idea across. In this particular example, the Pareto front consists of points A, D, and E. And you can see those sort of form an outer boundary there. In this particular example, we're looking at maximizing both Objective 1 and Objective 2. So we consider that as we go higher on the y-axis and as we go further to the right along the x-axis, we have our more desirable values for these functions. So if we look at some of the other points, you might ask, well, why aren't these other points on the Pareto front? So we have our answers here. So we see point C, Point C definitely dominates point B because it's better in both objective 1 and objective 2. However, point C is dominated by D, and therefore it cannot be on the Pareto front. Okay? Now, in a different kind of example, if we look at point E, we might ask, how did point E get selected to be on the Pareto front? Well, E obviously doesn't dominate any of the other points that are on this slide, but it does get put on the front because it itself is not dominated by any other point. Okay, so the Pareto front is the points that are not dominated by any of the other points. What this tells us in our design is that the Pareto front points are going to give us our best solutions for conflicting criteria. So the problem with conflicting criteria is which one do you choose? Okay, and we all face decisions like this every day. You know, do we buy a bigger car or do we get a car with better gas mileage? Okay, those types of things are often conflicting. Okay, do you pay more for item A or do you pay less for item B, and which one is going to give you the better value? By using the Pareto front, we're guaranteed that we have the best set of points possible for all of our different objectives. Now, the Pareto front points themselves are all considered equally good from a design point because they've all been selected because they are better in at least one of the values for their objective functions. Now, what happens is that at the point where you have the Pareto front set of designs, then we need to incorporate subjective measures to be able to tell which ones of these designs are going to be better than the others. And this would be an area for a subject matter expert, some type of engineer, to be able to decide these things. Pareto front also assures that reasonable trade-offs have been made among multiple objectives. Okay, so you're not giving up all of objective D in order to accomplish objective A. You have some reasonable trade-offs there. And the Pareto front points lend themselves to resilient designs. So if you're interested in picking a design that's going to be resilient to change in the future, because objectives are always changing for systems, then you have your Pareto points, and you're assured that if you pick a Pareto point for a design, then for future designs, you're going to get good value for making changes to that. You're not going to end up with something totally unworkable if you pick a Pareto point. So here's a simple algorithm. This is the algorithm that TC Falls actually implemented using R and C++. And so we sort the alternatives from best to worst using two of the objectives. Okay, so we're looking at the first objective increasing, and the second objective value is used to break any ties for the first objective. After the sort, the first alternative is always added to the set of Pareto points. Okay, and then we basically proceed sequentially down the list, looking for values in the second objective that are going to be higher than the values that were previously added to the Pareto front. Okay, all of these are added to the set. And if you're dealing with more than two objectives, like we are with LCAAT, because we have a set of 5 objectives, basically what you're going to do is end up taking 2 of the objectives at a time, performing this algorithm, and then at the end, you're going to take the union of all the sets that you found. And that's going to be the Pareto front for the entire set. So what does a Pareto front look like? We looked at a simple example, and we're going to look at some more specifically related to the LCAAT data. But first, if we consider a 2D optimization function where we're looking at cost and value, and this is a very typical scenario. You're always trying to minimize the cost, you're trying to maximize the value for something. So the minimum point that represents cost and the point that represents the maximum of the value that you have are going to be endpoints on the Pareto front. Now, these could be 2 separate points, but they could also end up being the same point. So if you have a point that is the minimum of cost and the max of value, that 1 point would be your starting point. And the Pareto frontier is going to fall between. So we're going to look at some specific LCAAT examples now. These are two-dimensional examples, and I see that they look fairly small on the screen here, so I apologize for that. But basically, all of the gray points are the design points. So we're looking at the LCAAT design, that 270,000 CSV file in two-dimensional space. And in this particular example, we're looking at the turn rate versus the cost. So we're trying to maximize the turn rate and we're trying to minimize the cost. Okay, so you can see that our Pareto points, which are the red ones, fall up in the top left-hand corner. So they're sort of clustered up there. You can see that we have a flat line across the top, which shows us that as our cost increases, we're not getting any higher turn rate. Okay, so this is why we're clustered along the left corner there. In this example, we're looking at the maximum speed of the LCAAT versus the cost. Again, we're looking to have the Pareto points clustered up in the upper left-hand corner. And here you can see something that's a little counterintuitive, which is that as the cost increases, the maximum speed in the design actually decreases. And here's another example where I've actually done 3 different levels of Pareto points. Okay, so what we've been looking at are the level 1 Pareto front points. What can happen though is that you can compute the level 1 Pareto front points, remove those from your design set, and then compute another Pareto front. Those become your level 2 Pareto front points. You can do it again and end up with level 3. So I did this as an example of showing 3 different levels of Pareto points. And this is actually the takeoff field length versus the cost. So we're trying to minimize the takeoff field length, minimize the cost. So I've blown up the little section in the lower left-hand corner so that you can see what the different levels of Pareto points look like there. And here is cost versus range, which looks a little bit more like what you expect a typical Pareto front to look like. There are also 3 levels of Pareto front points in this slide, and we're going to look at a close-up of those. So here's what it looks like without all of the other 270,000 something cluttering up the space. And here's an example of why you might want to look at different levels of Pareto front points. You can see here for one example, we have a cost of $1.31 million, and we have 3 different ranges for the level 1, level 2, and level 3 Pareto front points. So obviously, if you can, you want to take the level 1 Pareto front point. But remember that we're not only considering 2 objectives, we're taking into consideration 5 different objectives. So there may be some reason why this level 1 point is not going to be a good design based on some of the other objectives. So at that point, you may want to consider a level 2 or a level 3. And you can see here that you can get those levels at the same cost. Okay, so we've been looking at 2-dimensional Pareto fronts. So those were computed based only on the 2 objectives that were labeled in the graph. In this graph, we're looking at a 2-dimensional view, but the Pareto front points that show up here as red points were actually computed on all 5 objectives. So if we look at a little close-up of this, you can see that it muddies the waters. So if we're again looking at just the cost versus the range, then we see we have Pareto fronts all along the 2-dimensional area that's shown, not just along that left boundary. And here are some example 3-dimensional views. So here we're looking at the speed, the range, and the cost. Okay, and it's fairly obvious that we have clusters of Pareto points. Okay, so it may be useful for some designs to be able to pick out these clusters, be able to for some reason, analyze the Pareto points as clusters rather than as individuals. Here's another example that takes the turning rate, the range, and the cost, and if we rotate it a little bit, you can see again that we have clusters of Pareto points. As far as implementations in R, there are at least 2 packages that include Pareto front computations in them. There's an MCO package and an RPref package. The RPref package contains a fast implementation that was done in C++, and the implementation that TC actually did was implemented in R and C++, so it's a combination. And in preliminary timing studies, this algorithm was about 6 times faster than the algorithm implemented in the MCO package. So now we have our Pareto front capability. What we want to do is be able to use this within TradeAnalyzer, where TradeAnalyzer is a Tradespace analysis tool that provides a lot of functionality as far as visualization, filtering, all different kinds of techniques. But one thing it doesn't include as a primary feature is that of Pareto fronts. So in TradeAnalyzer, I'm going to look at the process here. To be able to use TradeAnalyzer, first off, you want to create a project. The project is created around a Tradespace. The Tradespace is just a CSV file like we have with LCAAT, 270,000 lines CSV file that's uploaded and converted to HDF5, which is a fast binary format. And at that point, you have your Tradespace in TradeAnalyzer, and you're able to use all of the different tools and techniques on the Tradespace to be able to perform an analysis with it. And you'll notice that the last bullet on the Explore side is the ability to have custom scripts. Okay, so the ability to customize an analysis is a very nice feature of TradeAnalyzer. You can upload custom R scripts, verification processes run on those scripts, then you can use the scripts on the associated Tradespace within your project, and within your R script you can create new Tradespaces, a subset possibly of the original Tradespace. You can have a Tradespace augmented with new columns and new data, or you can actually create plots that will show up in TradeAnalyzer. So here's a representation of the process of getting the Pareto front script into TradeAnalyzer to be able to use it along with all of the other tools. So local development is done in R. The R script is then uploaded and verified in TradeAnalyzer. At this point, the script is available for the project. So the script can be run on the data, the original Tradespace data. From the script, you can generate new data sets. In this particular example, 2 data sets were created, one that consisted of only the Pareto front points computed from the LCAAT Design data, and another set that consisted of the original data augmented with a new column that indicated whether each design point was on the Pareto front or not. And at that point, you have new Tradespaces, and you have available to you all of the tools and techniques from TradeAnalyzer to produce plots, filter the data, and do all sorts of other things. And here are some 3D views of the same data that we looked at plots earlier, but these were actually generated from TradeAnalyzer. So here we have the range versus cost versus the speed. The larger red points indicate the Pareto front points, and the smaller blue points indicate the other points in the design space. Here's another view of that same data set. So before we were kind of looking at it from inside the cube, and now we're looking at it from the left outside wall of the cube, where you can easily see where the Pareto points are clustered. And here we've used another feature of TradeAnalyzer, which is the opacity. So we have the capability to represent data in 3 dimensions, but if you remember, we have a 5-dimensional objective function. So how do you get that extra information visualized? Well, one of the techniques in TradeAnalyzer is to use opacity. So here we have the same 3-dimensional variables. We have the max speed, the cost, the range, but we also have the points using opacity colored by the turn rate. Okay, so the darker points have a higher turn rate value, the lighter points have a lower turn rate value. Okay, so now that we have the Pareto front generation for the LCAAT design data, we want to look at where we want to go next. So to look at where we want to go next, we have to determine where we are. So where we are is that we have a design space. From the design space, we've generated a trade space. The trade space is then reduced by using Pareto front, potentially other techniques. Now at this point, the reduced set of design points are sent for mission effectiveness measures. Okay, and this is where we get into modeling and simulation software such as AFSIM, Combat 21, other types of things like that. The problem with this workflow is that you've already reduced your design options before you get to mission effectiveness. And if you recall, one of the features of set-based design is that you delay your design decisions as late as possible in the process to be able to have as much information available to you to make good decisions as possible. And in this case, we're actually reducing the design space before we're able to tell how the designs are going to perform in their missions. So current and future work is to take the first 2 steps as they are, but instead of reducing the design space before using measures of effectiveness, we want to use HPC resources and take all of the TradeSpace designs, the 270,000+ designs, run them in mission effectiveness software, and from that point, we want to augment those measures of effectiveness with the TradeSpace and then perform our design set reduction at that point when we have more information available to us. These are some of the resources. If you need more information on any of these topics, you might find some here. And other than that, that's all I have for today. I appreciate all of you coming out today. And if there are any questions that I can't answer, TC Falls is in ICER. I'll be glad to give you his phone number, his email, his address, whatever else you need. Thank you.
An observation with my question. The assumption that all the objectives are weighted the same, all 5 objectives. So if you change the way that your objectives, say cost is more important than flight altitude or current rate of turn or speed, then it seems like you would add almost like a 5-factorial multiplier to the solution. So how would you analyze it, and then would be really
Well, what you could do is build that analysis into the objective function itself. And so that when you're computing your cost, you can add the multiplier in for your cost, and so that becomes part of your objective function. Or that's my answer anyway. Yes?
I may have zoned out, but I looked at one side, I realized you're talking about the different levels of Pareto points.
Yes.
I missed what the levels were, where that came from.
Okay, so generally if you just compute Pareto front, you're talking about a level 1. So you're talking about the entire data set, you compute the Pareto front, those are level 1 points. The level 2 comes in if you remove the level 1 Pareto front points from the data set, compute it again. It's like a second derivative, you know, derivative of a derivative. So, yes.
Kind of follow on from Jeff's question, can you slide point over here to give us an example of how those second and third level Pareto fronts can
I will attempt to answer that, but since I'm not a systems engineer, I can't tell you for sure how that would be useful. Just sort of intuitively speaking, if I can ever get back to the slide. Almost there. Okay. So, here. Okay, so what I was saying was that in this particular slide, these Pareto front points were generated only from these two dimensions, okay, not from all 5 objectives. So when you look at it from this point, maybe an engineer has a particular reason for wanting to look at only the 2 dimensions isolated from the other 3. Okay, so in looking at these, the level 1 Pareto front would probably be the one you want to choose in isolation. But when you're looking at objectives combined from the other factors, there may be a reason why you can't pick that level 1 Pareto point because of the other objectives. And so at that point, you may want to remove those and see, what about if we go to a level 2? What about if we go to a level 3? Do these Pareto points fit more in with optimality when considering all of the objectives? Do they give us a design that we can use or not? So again, systems engineer would be a better person to say whether that's a practical thing to do or not.
So your initial set of data points that you're doing the Pareto front analysis on, how do you know that you've sufficiently sampled that space?
It's not sampled. All of the designs are evaluated as being on the Pareto front or not being on the Pareto front.
No, like how do you get that? If you go to your initial table, so you've got all of the different design considerations, and there are different parameters in those design considerations. Is it an exhaustive sample of every?
So how are you asking how the design space was generated in the first place?
Original design space.
Okay,
The full
so
design space.
so the full design space in this case for LCAAT was generated. The design team, it was a clean sheet design team. They came up with 9 design variables. On those 9 design variables, they ran a multi-objective genetic algorithm. And I want to say they went for like 900 generations. And in those 900 generations, that produced the 270,000 set of designs based on those 5 objectives. That's how the design space was created. Now, it can be created by doing a full factorial. You just take all of the columns and you do every combination of all of the valid values. That falls into design of experiment, sort of. So we didn't question how they generated the design space. You know, our job was basically to evaluate it once they got to that point.
Great presentation.
Thank you.
I wanted to ask, at the beginning you were talking about how one benefit to set-based design versus point-based design was that you had a more robust, less brittle design selection. But what it seems like, and I just want to make sure that this is consistent, that with this process, you go beyond just having a design selection, but an analytical process. So if you have some change in your specification, you no longer just have the design to tweak, you have the analysis to go back to, for example, and change the priorities.
Right, and you have other designs that you can go back to and say, what if we move from this Pareto front point to this one? What does that give us?
The design parameters, you have 9 design parameters, and they are just for one particular product, correct? Or
Yes.
they are for, in your example, for multiple types of aircrafts.
Their design possibilities for one potential aircraft.
So you explained the objectives, how design space was generated. How about the cost? So for each that function, multi-objective function,
Included
also
cost.
generated the cost?
It,
So for
you're asking how the cost was generated? They have their own cost formula. So based on the design parameters, they're able to determine what the cost is.
So you got this design space from that?
Yes, yes. We were not involved in the generation of the design space. Jeff?
I'm a little surprised at the future path here because, okay, the idea of, it seems to me that one of the ideas of being a Pareto front is that you eliminate a lot of the work you've got to do. But doing the evaluation, the M&S evaluation of the design is not an inexpensive operation. I think somebody can correct me that knows very expensive. Yeah, it can be very expensive. So it seems to me that one of the ideas here is you want to cut down your trade space significantly before you start doing that. And now you're saying, no, we're going to go ahead and do the evaluation on the entire trade space and then go back and.
Well, the idea is to utilize HPC resources. So what's expensive on a desktop is not as expensive on HPC in terms of.
It's still expensive. You just put the cost somewhere else. But,
Okay.
I mean,
I can go along with that. But the purpose is you could come out with a very different answer if you incorporate measures of effectiveness into your design considerations before reducing the design set. You could come out with something that works a lot better in the real world. So maybe that's worth the extra cost, maybe it's not. I don't know. That's just the theory right now.
I have another question regarding design. I'm sorry.
Mm-hmm.
Most of the design parameters may change quite often, in a matter of 2 years or so. So if the solution that you obtain is a 2-year time frame, but new parameters come to light, new formulations, so on and so forth, to have a better or more optimal design, would you rerun the?
That's a little bit out of my realm. That's more into creating the design space and the systems engineer who developed the design parameters. So I can't say really whether the runs that were generated without those new variables are going to be useful or if everything has to be redone. If that's your question, I don't know. Most likely, I would think. Josh?
So you said Pareto fronts help to find resilient designs. How does a Pareto front help determine an outlier from a more standard point?
Well, a Pareto point, remember, a Pareto point is always going to be one that there's not a better design for with regard to at least one objective. So if you have a Pareto point, even if it might be considered an outlier, if you're looking at standard measures, you're still guaranteed that that point is better in at least one respect to the other points. Is that kind of what you were asking? Okay.
Just to follow on to Jeff's question, is there any plan to evaluate the effectiveness of performing those recomputing simulations before doing the Pareto front analysis? By
Yes.
comparing the Pareto fronts that you got before and after?
Yes.
See
Yes.
if you're actually getting a difference?
Yes, that's kind of the plan.
Okay.
Ruth?
Yeah, how much time does this Pareto from our intake to get for those that are 270,000?
A couple of seconds. Couple of seconds. Okay, you don't push the button and instantly get the answers, but you also don't get up to get a cup of coffee. So, yes.
How does Pareto front, how is it affected by error or variance?
That would be a TC question. So, I can't help you with that.
It's also
But,
the reason why you do a second and third level work in order to account for some of that variance that's going to occur within your calculations. But the variance is going to differ depending on the models
Well,
Is that a measure of conversions of your solutions?
okay, so the actual graph is kind of misleading because all of those that we showed in the 2D plots, it looked like it was only a couple of points, but it was actually many more than what it appeared to be. Because when you're varying the design parameters, the 9 different design parameters, you can think of those variables as being swept in terms of input values. You're going to end up with duplicate values when you're looking at only 2 of the columns. Okay, so each point could actually be representing many more than that. So it's more points than what it appears to be in the type of graph that was shown.
It's probably a system level question. Say you, in your previous workflow, you calculated the Pareto front, and then you find out through the simulation that it's not very effective. Doesn't that indicate a problem with the model to begin with?
It could. No, Simon says no.
Not necessarily, because something can move faster doesn't necessarily mean that it's going to provide a positive impact or effect on the battlefield. If it moves twice as fast as every other system on the battlefield, then it's not mutually supported. It may not be what you're looking for to accomplish the overall mission. So even though it may still be the best physically based design for that system, in the overall system of systems that it has to operate within, it is not the most effective, it's not the most important system that you want to put in place. And that's why running effects-based simulations before you're using Tradespace is something we're investigating, because we want to make sure that we're not just picking the best system based off of, hey, it's fastest, can carry the most weight, it's the cheapest. Well, those may not necessarily be what you're looking for in the handheld battle. If you're looking at a military system.
Okay, well, thank you very much.
The presentation, the video we just recorded and the slides will be available in our ERS wiki. We have a link to the Erudite Science Series in our wiki. I'll be sending you an email with the link, but if you want to go find it, it's ers.wiki, wiki.ers.hbc.mil. There's a link to the ERS Knowledge Bank with all our training, all our presentations. Tons of good stuff up there for you. So you'll be receiving the link. We'll have this up here next week for you to review and reevaluate. Thanks.
Thank you, Marty.